Okay, so now we're moving on to arc length, okay, which is 8.1. And arc length really, let's start right here. Let's do this, okay? If I have any curve of any kind, okay? If I break up the curve into a whole bunch of little line segments, that is how we would find the length of this arc. And the distance for each one of these line segments, we would use the distance formula. And the idea is to get an infinite number of line segments, right? So I'm going to say n is the number of line segments. And really, we want these line segments to be really small. So, of course, we want them to go off to infinity. So I would say arc length, which I'll denote as capital L, is equal to the limit as n goes to infinity, I equal to 1 to n, the sum of all of these distance formulas between every single one of these points. Okay? So this is my change in x, this is my change in y. If I say I equal to 1, this guy, minus then the previous point. Here's y, and then minus the y of the previous point. So here are my 2 points. My 2 points, my first point here is I minus 1, and these are the coordinates of I minus 1, these two right here. And this is my next coordinate, pi, and these are the two coordinates of those. And so using these 2 coordinates, that is how we set up this distance formula, okay? Which we can easily simplify to this. How is this done? Well, we know that when we take any difference, that means change, and we're doing the change in x, and we're squaring it. Now, this is equivalent to the change in y, but since we're doing the limit, this will be dy, right? And so we learned back when we were doing differentials that dy is equivalent to f prime of x times delta x, or f prime of x times dx, or dy dx times delta x, and so on and so forth. We learned that it's all of these things. So to keep the terms the same, I just replace this expression, which is these guys, and I replace that expression with this, okay, which is this one right here, okay? And I did that because I want to have my 2 delta x's. Now, this squared gets distributed because these are multiplied together, and so now, since both of these terms have a delta x being squared, I can factor out a delta x, and I can also pull it out of my square root because that's squared, so it will leave me with just delta x. And so now, what is this equal to? We know that the limit with this sum gives us an integral. And I'm going to say x equal to a to x equal to b. And then I have this expression right here. And so I will bring it down here. And that is the same as this. Okay? They're exactly the same thing. So you would probably want to put this on a flashcard. Okay, this is your arc length formula. L, arc length. Okay? So now, we start off with this problem here. Find the arc length of this curve here between the points, this point and this point. Okay, so going according to our formula that we had, what are we going to need? Actually, I think I have that right there. I have it right there. Okay, just ignore that for a second. Okay, this is my formula I start off with. And I realize, hey, okay, I can get this in terms of x. So I'm going to need my derivative. Okay, that's all I'm going to need. I'm going to need to square it. So first I need to get in terms of x. So I solve for y. Then what I need to do, I need to take the derivative of that. So when I take the derivative of that, it ends up being that. Right? And then I need to take that derivative and I need to square it and put it right there. So I square the derivative, and that's what I get when I square the derivative. And so now I'm going to take this information, I'm going to put it into my integral. So here's my integral. Now, since I'm in terms of x, what x coordinates are we going to? From 1 to 4. So from 1 to 4. Square root of 1 plus, and then I'm taking this and I'm putting it into my formula. And then we integrate and we realize, oh, we have to use substitution. No fun, but oh well. And we say use this, so therefore du is that, and then divide out the 4/9 or 9/4. Excuse me. And we get that. Okay, and then of course we have to change our limits of integration because that would be bad if we didn't. Because we're in terms of u now, okay? I'll write u is equal to. So we remember these things. Okay, and then when we find the antiderivative, undo the power rule, we have that. And then this is what it is, simplified. It might take some time. And yes, it is yuck. Okay, but that's what it is. And then we took the liberty of putting that in the calculator just to see what that ends up equaling. And there you have it. And this is units, not units squared, because what are we doing? We are finding arc length, and that's going to be measured in units. Okay, so that is what you get. So that is the arc length. Now, we also tried to do this in terms of y, because whether you do it in terms of y or you do it in terms of x, it's not going to matter. It should end up being the same thing. So if we do it in terms of y, what changes? Well, instead of having f prime of x being squared, we have f prime of y being squared, and it's going to be dy. These are going to be y's. So you're going to look at your coordinates from 1 to 8. From 1 to 8. Okay? And then, in this situation, you're going to solve for x. So we solved for x. Then we took the derivative of that. And then we squared the derivative, which is that. And so then when you substitute that into your integral, you get this expression, which we thought was way too torturous for us to sit there and integrate. So what did we do instead? We used our calculator. Yeah. And we found out that, oh my gosh, it's the same thing as it should be. And so we are proud of ourselves, okay? But this is how you do arc length, and this is how we derive the arc length formula, okay? All right, good luck.